In this recording, we're going to be focusing on the fuel source for skeletal muscle fibers or our muscular system. Ultimately, we're going to be interested in ATP. ATP is that all-important energy currency of the cell. All contraction depends on ATP, and to a lesser degree, relaxation of our skeletal muscles also depends on ATP. So as we look at ATP, think back to our chapter 26 discussion on the carbohydrate metabolism. Our ATP depends on oxygen and organic energy sources. Most of the time, we're going to be getting our organic energy sources in the form of carbs or glucose. To a lesser extent, we can use fatty acids or amino acids, but we need that oxygen. So we can make ATP two different ways. We can have anaerobic respiration or fermentation, and we can make ATP when we don't have enough oxygen. There's very little ATP that's going to be made, though, and there's going to be that lactic acid or lactate as a byproduct, which we need to pump into the liver to get rid of. Anaerobic respiration is less than ideal, and this is typically what you're going to be doing when you're doing endurance exercises with your muscles. We can also have aerobic respiration, and these aerobic methods of respiration produces a lot more ATP and does not generate lactate. The downside of this aerobic respiration is that you need to have typically enough oxygen supplied to the muscle. So we're going to talk about what we do when we don't have a lot of oxygen available and when we do have a lot of oxygen available. So as we're looking at aerobic respiration, we have lots of oxygen available, and the guy can run, and he's doing great. We have lots of oxygen in the form of myoglobin within the skeletal muscle fiber. And then as the guy is jogging along, we're going to shift over to the phosphagen system. And from that phosphagen system, which takes about 10 seconds-ish to hit into, afterwards, we're going to initiate the glycogen lactate system, aka anaerobic, low oxygen or no oxygen fermentation. And that's typically going to be after about 40 seconds of strenuous work. And then finally, we're going to have this individual continue to work out, and his body is going to have to find his rhythm or their rhythm. And in this situation, this person is going to have to find a steady pace where his lungs are able to deliver enough oxygen to his body, and he's not going to consume oxygen faster than he needs it. So this is one of the reasons why typically sprinters can move really fast, because they have a bunch of extra oxygen stored in their muscles. But when you look at distance athletes, they have to slow down because they're depending on the rate of their oxygen delivery via their pulmonary system. So when we look at short, intense exercises or sprints, we're going to have the myoglobin molecules that supply oxygen. Our muscles are going to have ATP just floating around naturally. And we also are going to have ATP being borrowed from phosphate groups. In particular, we have high energy molecules that can store phosphate and then dump those phosphates onto an ADP, adenosine diphosphate. And then an ADP is going to be rapidly turned back into an ATP. Two of the enzymes that are responsible for these phosphate transfers are myokinase, myo meaning muscle. Kinase refers to a generic, let me pause for a moment here. Whenever we think of kinases, this is kind of a generic name that refers to an enzyme that moves phosphate groups around. So a myokinase is going to transfer phosphates within a muscle cell, and it'll take an inorganic phosphate from one ADP to another, making an ATP. We also have creatine kinase. Creatine kinase is going to have a phosphate storage molecule called creatine phosphate, and that creatine phosphate donates an inorganic phosphate to ADP, turn it into ATP. We're also going to have our phosphagen system, and this phosphagen system is going to depend on a combination of ATP and creatine phosphate, which provides nearly all the energy needed for short bursts of exercises. So we have 6 sets of sprinting fully supplied by the phosphagen system. So to reiterate what we're talking about, we have the myokinase. Myokinase takes one phosphate from one ADP and adds it to another ADP, making the second ADP into an ATP. And then we can have the creatine kinase. Creatine kinase is going to take an inorganic phosphate from creatine phosphate, transfer that inorganic phosphate to an ADP, forming ATP as a result. This phosphagen system, this way of regenerating ATP directly from ADP, is short term. And as our phosphagen system is exalted, we're going to shift over to anaerobic respiration. And in these situations, the an meaning without, our muscles are going to need to use glucose from the blood and or depending on how much glycogen is present, there's stored glycogen that they have. And when we don't have enough oxygen present for cellular respiration to occur, particularly the electron transport chain and the citric acid cycle, all we have left to rely on is glycolysis. And we'll have a net yield of 2 ATP for every glucose molecule. That's review for you at this point. That glucose then ultimately will go to pyruvic acid, and pyruvic acid will go to lactate. And that lactate is going to keep building up in our bodies. Eventually, we can detect the lactate in our bloodstream. And once we hit that point where we have lactate detectable within our bloodstream, we've hit our anaerobic threshold. We also are going to have a glycogen lactate system. And this is a pathway that we can use where we can take glycogen to lactate and back and forth. So we're looking at this glycogen lactate system. We're going to take glycogen, which is a whole bunch of glucose molecules linked together, and convert it to lactate. And for every one of the glucose that's present within the glycogen, we'll get a net yield of 2 ATP. And this glycogen lactate system, which occurs in the skeletal muscle fibers, produces a decent amount of ATP. So we can have 30 to 40 seconds of activity powered by this particular method of ATP generation. However, after about 40 seconds, so after sprinting for about 40 seconds, you don't have any more short-term fixes. Now, all you're left to depend upon is your respiratory and cardiovascular system. And you need to have good lungs and good circulation to get that oxygen to your muscle cells where it's needed, and you'll shift over to aerobic respiration only without any of those short-term backup methods to help you out. And in this situation, usually the overall net activity of the individual is going to go down because they don't have those short bursts of ATP from those previous systems we just talked about. We're only dependent upon the ATP that we can generate as we're delivering oxygen to our muscle cells. Aerobic respiration will produce more ATP per glucose, 32 to 34 to 30, a little bit more than 30 ATP per glucose. It's very efficient. The downside is, though, that we and I'm thinking of me, myself in particular, a couch potato, I push paper for a living. I don't have a very efficient cardiovascular and respiratory system because I don't exercise like I used to. So for me in particular, I have a hard time delivering oxygen fast enough for when I want to compared to what I actually want to do. So after we look at an average person, in 3 to 4 minutes, oxygen consumption will typically level off and equalize with aerobic ATP production. So when you think of those individuals that can run a marathon in less than 3 hours, they have a very great and a very excellent cardiovascular and respiratory system, and they can deliver oxygen at a very high rate. People like me who don't do endurance running, we don't have the ability to deliver oxygen as quickly, so my rate of ATP consumption is going to be lower, and ultimately I run slower when I do distance running. So I'd be more of a 5 to 6 hour marathon time if I actually tried to run a marathon, which I probably wouldn't because it would hurt my knees too much. As we're looking at that 30-minute mark of exercise, we're typically going to find that we shift from glucose to fatty acids. So for those of you who are trying to get rid of love handles in particular, you need to typically have about 30 minutes of exercise before you shift over to consuming fatty acids, or 30 minutes of a glucose shortage before you shift over to fatty acids. And remember, we're really good at storing glucose in our bodies. And then anything beyond that 30-minute point is going to focus primarily on fatty acids and a process known as beta oxidation to produce our ATP. So if you go for a 3-hour bike ride, maybe, while we're practicing social distancing and the safer at home thing in Wisconsin, thanks to COVID-19, we could go for a long bike ride and you could focus on burning those fatty acids after you hit the 30-minute mark. So as our muscles are starting to wear out, we have something called muscle fatigue. We think of muscle fatigue as just weakening of our muscles, and it's an increase of weakening or progressive weakness that occurs as we have physiological changes within our skeletal muscle fibers. In particular, we have potassium building up within the T-tubules. And as potassium builds up within the T-tubules, we're going to have reduced excitability. We're going to have a harder time stimulating the sarcoplasmic reticulum, the terminal cisternae, to release calcium ions. We also start to run out of ATP. And instead of having ATP, we're going to have lots of ADP, and lots of extra ADP slows down the cross-bridge movement. ADP can competitively compete with ATP for the myosin heads. We also find that calcium release is going to be reduced, and ultimately the force production within our myofibrils goes down because we're running out of ATP. So as we're thinking of this fatigue, it typically can result from lack of fuel. If we run out of glycogen and glucose, if we don't have enough electrolytes, as we're sweating, we lose sodium, we use potassium, particularly we lose a lot of sodium. And for the record, you need to have a lot of sweating for this to be a problem. Most people get plenty of electrolytes in their diets. We also could have central fatigue, and this central fatigue is kind of unique. When we think of central fatigue, this is the degradation, the inability for us to make more action potentials within our motor neurons, because our skeletal muscle cells are going to be releasing a chemical known as ammonia as a byproduct of all of these contractions and burning through all these energy reserves. And as ammonia enters the bloodstream and ultimately the central nervous system, it's going to change the chemical environment of our central nervous system and make it more difficult for our brain to initiate action potentials on the motor neurons. Also, there's something called willpower, grit, motivation. As people are exercising and continue to exercise, their levels of discomfort go up. Some people have very low thresholds of pain tolerance and they give up really quickly. Other people can just go and go and go and keep running until they cause lots of damage to their bodies. Why some people give up right away and why some people keep working out until they cause lots of tissue damage is not very well understood. Thankfully, most of us are somewhere in between those two extremes. Another factor is going to be the ability to deliver oxygen. If we can have a high rate of delivery, we can have a high rate of ATP generation. So our VO2 max, the rate that we can uptake and deliver oxygen into our bloodstream, is very important. So how do you measure VO2 max? You can typically measure it when the rate of oxygen consumption plateaus within an individual. So in order to test for VO2 max, you need to measure how much carbon dioxide that person is giving off. And carbon dioxide emitted by a person directly correlates to the burning of oxygen. Think of that all-important chemical equation I had you memorize for carbohydrate metabolism. C6H12O6 plus 6 O2s yields 6 CO2s and 6 waters. So by measuring the carbon dioxide that comes out of a person, you can calculate the amount of oxygen being consumed by that person. And thankfully, it's a 6-to-6 molar ratio between the two, so the math is really easy. Generally speaking, bigger people have higher VO2 maxes. Bigger people have bigger lungs can deliver more oxygen. Most of us are going to have our VO2 max peak around the age of 20. And after 20, it starts to slowly go downhill. It's almost always going to be greater in males. In particular for males, that testosterone has caused their their skeleton to expand, and they have those larger frames, the larger thoracic cavities, and the larger lungs within those thoracic cavities. So we're going to have a higher rate of delivery of oxygen, a higher VO2 max, typically in most males compared to most females. And yes, there are exceptions. And then we can find that in endurance athletes that are in peak condition, so somebody who has a genetic predisposition and who's working their tail off and exercising, can have a very high VO2 max, typically twice the VO2 max compared to an untrained person. So whether or not you have a naturally high VO2 max, you as an individual can influence your VO2 max with your own lifestyle decisions. Are you choosing to exercise, or are you choosing to be a couch potato? We also can have excessive post-exercise oxygen consumption, EPOC for short. And this is the phenomenon you find when people, as they're running, they cross the finish line at the end of the race, and then they huff and puff for 4 or 5 minutes. The reason they need to huff and puff, even though they're done contracting their muscles, is because they have an oxygen debt. What's an oxygen debt from? Well, we can have an oxygen debt because they have a shortage of ATP in their bodies, and they need to burn through a whole bunch of oxygen when they're done exercising just to regenerate their ATP. Some of that ATP goes immediately to regenerating creatine phosphate reserves. Some of the oxygen in their body is going to be used to reoxygenate the myoglobin within the skeletal muscle fibers. Some of the oxygen is going to be used to turn lactate back into pyruvate within the liver. So our liver is going to be a big oxygen suck after we're done exercising. And we're also going to use a lot of oxygen to get rid of the metabolic waste that have built up in a lot of the cells of our body. So if you look at our excess post-exercise oxygen consumption, the EPOC, we typically find that it's going to be 6 times the basal consumption. So think of that person who's been exercising really hard. They're going to be breathing really hard and using up oxygen about 6 times faster compared to the couch potato, or that individual when they were just sitting on the couch chillaxing. That's all we have for this recording. We discussed different ways of making ATP and different ways of getting rid of waste within our skeletal muscle fibers or skeletal muscle cells. As always, if you have any questions, please feel free to post them on the discussion board, shoot me an email, or ask a classmate. And happy studies.